like the right answer. Yeah. It'll be fine. The inverter, or the ELAD's problem was kind of easy because everything was inverted. The last one. I was studying this, like this exercise last week, and I just realized there was one from last fall where the clock was inverted.
Oh, yeah.
All right, guys, listen up. But I want to show you something. I sent this to everybody, and this is going to be really valuable. And this will be something you're going to be need to required to know and know how to do later on, especially on the final, all that stuff. Something related to this. Now, I gave you. I know you had a test in visual electronics.
Yes.
All right, I'm doing well. Now that that's done, I don't know if you did the homework or not, but what I did was assign something where we actually had, using that relationship I showed last time, where you can take really e to the j, you can take quantity 1 minus e to the minus j omega t, or j omega, divided by j omega times the actual dtft, or dft of something that you can get on MATLAB and compare it directly to the Fourier transform. Do you all remember the lecture? Right? Well, this was one of the things that yours could do is actually do some of the comparisons. Now, let me just show you what I'm up to. I don't do this normally, but this is a very important part of the class to see this. Here, I've defined a function. It's a very simple function. It's e to the minus at, where a is given here as 1. And it's defined between the ranges of 0 and tf. Now, I want to show you some things about MATLAB. How many have used MATLAB before? Has anybody not used MATLAB? I see we have people that are not responding. That's okay. You all are going to need to know how to use MATLAB in your upper level courses especially. And you'll find it very valuable and very powerful. And I think I said this before. Correct me if I haven't. Everywhere I've been in the last 25 years, I've been here about 33 years, in the last 25, all the basic prototyping was done in MATLAB. Now there are things that are free that are just about the same as MATLAB, and they parallel MATLAB. One is Octave. It's completely free. You can download it. Jeff can keep me up. Jeff has done a lot of software engineering with network services. He knows more about what's available right now. Octave's still free, isn't it?
Yes.
Octave is good. Now Python is free as well. Python is a little more clumsy to use, but it does a lot of things MATLAB does, not with the efficiency or the high performance toolboxes. All the stuff I've ever done, when you come up with an algorithm for pulling out Doppler data from a radar signal, the first prototype is almost always in MATLAB. Once you get it perfected, you can take that code and turn it into a C++ code or a C# code or even a Fortran 90 code, something that's allowable, and you can have it in the actual compiled form that's used. And it's very efficient. Now, I say that because MATLAB usually gets a lot of pushback from students. There's a learning curve with MATLAB. Here's a tip. You want to learn MATLAB? Get on YouTube or get on Google. Really, YouTube's the best. Just type in whatever you want to do and see, and there are usually tons of people more than willing to explain everything you want to know. So, having said that, this is the little script I did, and I'm going to explain it. In the beginning, clear all gets rid of all the stuff in memory. CLC takes what's called the actual, this is the workspace, and it makes it clean. I'm going to show you this in a second if I don't have it. TF here is just a constant. Now you'll notice how I have a semicolon out of all these things. See that? Can anybody tell me what the semicolon does? It prevents it from repeating itself. Let me just go to this workspace and show you what I mean, suppose I say A equals 5, just for the heck of it. Not even running. Are you kidding me? Busy? This is the one thing I hate about having this FlexLM license. You know what's going on, Jim? Upstairs it worked perfectly. Now it's not. All right, let me try this. There it goes. You see how it repeats at A5, pops it up again right there? Let me do it again. And if you ever want to get back to where you were, you just hit the up arrow and the last command appears. All right, 8 equals 5. Busy? There it is. See? And it keeps on repeating it. Well, it gets irritating. So you put a semicolon off after that. If you do this, with a semicolon, it better not repeat. Sorry, it's semicolon, not colon. Then it doesn't. Semicolon. Now it doesn't repeat. And if you hit A here, you'll see A is 5. Over here, you can see my workspace. I have everything stored in memory. These are the values, and it shows you the actual size. This is in the workspace. Now this that I'm running here is in an editor right here, and this is something called a script or an M file. It has a .m extension. It's continuous time Fourier transform to discrete Fourier transform, and it's showing you the relationship. So clear all will clear everything. CLC closes, CLC takes the workspace and brings it back to its, it'll clear this. Just watch this, it better at least. CLC, everything goes away. You're back to a blank page. So that way you'll know everything that's going to be on that workspace is going to be relative to the operation you do after CLC. You won't have a bunch of garbage in there. Now getting back to this. I'm trying to make this as useful as possible. If I did this and put clear all, CLC, and then close all, you'll see it'll close all the plots. Now there's a plot up here, hopefully right there. When I hit this, it'll get rid of it. I can actually type it right here in the command line, you'll see this. Just close all. Went away anyway. That will take care of that. Gets rid of it. So, in the editor here, I'm not going to put close all because I want to leave that plot up. Follow me, guys? And I want to let you see it change as things happen. Now, the next set of stuff is just values of data I'm going to use. I'm going to have a number of data points that have to do with the number of samples I'm going to take. It'll always be 2D for me. N here is 6. It's a small number relative to most computational stuff, so I'm going to have that many sample points. I have A as 1, and now I define this T. There's a lot of ways of defining things in terms of these as a string variable. It's going to have a whole set of values in one row or one column. Doesn't matter which way you do it. Here, I'm defining T in terms of something called a lin space. Lin or linear spacing between points. The actual points, the range of T is between 0 and TF. Do you all see that, 0 to TF here? Now my TF I have is 16, that means 16 seconds. Are you with me? But I'm not going to have just 16 values. What I'm going to have is NUM values, or 2 to the nth values. So it's going to take this range from 0 to TF, and it's going to chop it up into 2 to the n values. And I could literally put 2 to the n here if I wanted, and then I would define n here. I could do it that way. Follow me? But I chose to define the num right here. Now, then I define my function. X is going to be evaluated at each one of those points. You'll notice I just put t in there. I don't have to write a for loop or anything like that because t is what's called a vector. So x will be a vector. It'll have the same dimensions as t, I believe, in this one. If t is going to be a 1 by n vector, then the value x will be a 1 by n vector. Do you follow me? Now MATLAB's a vector, it has to do with vector operations, and it's important, and I'll show you some of the things where you have to be careful about. Next thing I do is say that I'm going to index something called k, and k is going to be the thing that would be used in a frequency domain to do the counting steps. Remember, when we're going to do a DFT, we have what? We have not x of omega, but x sub k, right? Where k goes from 0 to n minus 1 values, right? So here I'm defining the k index. And if I have n values in the time domain, I'll have n values in the frequency domain. Follow me on that? That's important. So here I'm just indexing it. You'll know I start at 0. The semicolon is the thing where I'm going to count. I'm going to go from 0 to the number minus 1, or k minus 1. And that's going to be, this semicolon means it's going to count from, or start at 0, end here at num minus 1. And that would be the values of k. Follow me? Everyone? Now I have something, I call this TS. This is the sample interval. Remember, I have TF is the range from 0 to TF, or 16 seconds the range. The actual delta t, the sampling interval, will be that divided by the total number of samples, or divided by num. You all see it there, class? If you haven't done this, just listen up. I'm trying to make sure you see this, and I don't want to rush. So that's going to be the number of samples. Here's one thing you can do, it's nice. I do this a lot in codes when I'm just starting to develop. If you put a percentage sign, it turns green. Anything after that is a little note to yourself. It's all like a comment. So I'm going to put this right here is sample. Or really call it spacing. You can leave it like that. Now, when I define x of n, it's going to be just x. You'll notice I have x defined right here, and now I'm defining x of n as that. The reason I am is I'm going to take the DFT of x of n, same thing as taking the DFT of x. And then I have w. Remember when I showed you how to do this last time, I said that now your omega, I should put an omega there, but I don't feel like scripting right now, I'm doing Greek. Remember, that omega is now going to be the omega where it's going to be discrete. It will be just like the Fourier transform omega, but it will not be at a continuum of values, but at discrete values. And remember how to get that. You take 2 pi over the number of sample points. It's like 2 pi over n. Then you're going to multiply that by k, because that will be the index from 0 out to the number of points you have. And the actual spacing would be divided by ts. And that will give you the exact frequency. Then I go ahead and I say, now, this is how you take the DFT. Well, I'm sorry. Once I have that, do you see that DFT equals FFT of x of n? You all see that? That's literally taking the DFT of the signal, the e to the minus at sampled at those points. Remember, that's a vector, and it has 2 to the n points. And it's literally taking the DFT of that. If I just presented that information, it would be meaningless to you. I'm going to do that, but I'm just showing you what this code's about. But if I go ahead and did what I showed you last time, we take 1 minus exp of this omega. Now this is scaled, right? According to that, times ts, and divide it by j omega, and times the DFT. Now I get something I can directly compare to the actual Fourier transform. Now, I know, and you know, that the Fourier transform of e to the minus at is what? 1 over a plus j omega, correct, class? You see that right there? I have the xf, I could put continuous time Fourier transform, but I just put it as xf is 1 over that. That's the actual transform. And if we use that scale value of omega, that would be the actual Fourier transform of e to the minus at, right, times u of t. Do you all agree with that? Now remember, this is a sampled signal. It's finite dimensionally. Now I want to compare these two and see how good the comparison is between this, the actual Fourier transform, and this, the DTFT, adjusted by the factor 1 minus e to the minus j omega t divided by, ts, I should, divided by j omega. So now I'm comparing them. Did anybody do this, by the way? Did anybody run these programs I gave? No one? Not us all. Well, hopefully we'll learn something. You'll be doing that. When I compare them, you'll notice there's a plot command. A lot of this will just fly by you. You won't appreciate it until you have to use it. Whenever you're plotting in MATLAB, you always put the horizontal variable first, it's omega, and then the vertical variable. I'm taking the absolute value of the actual Fourier transform, xf. This is this one right here. Then I have to put comma. Now I'm plotting another function on it. It's versus omega, horizontal. ABS of, now it's going to be the adjusted DTFT. And these things should compare exactly if you have a large number of samples. All right? And there's, what was the condition last time I said for this, the comparison that worked? There was one critical condition when we're sampling a function. Do you remember? What? The value of the function x of t has to change only a very small amount between samples, right? If it changes a large amount, this is not a valid. So therefore, the sampling frequency, you're used to thinking just twice the highest frequency of interest. That doesn't work. Now you have to sample such that the variable change, the average change per sample is going to be very small, usually less than 1% or 2%. if you want this comparison. The real problem is when you accidentally sample where a function goes through 0. All right, that's where you throw that point away, because 0 times 0.095 to see what the realm of the next sample value is, it's still 0. That's how come anything that has to do with the 0 you toss out on this one. You talk about the average change of the function during the sampling interval. And there's more to this, but I'm just trying to make sure you see the general stuff. So now I'm going to actually run this and we're going to talk about it. I'm going to go down to 4 here. This will show you a big change. And let me actually do something. Dimensionally, I'm going from, see this axis right here, this command? This talks about the horizontal spread of axis and the vertical spread. The horizontal is from 0 to 100 hertz. Well, if I'm sampling and I only have 2 to the 4th spaces, I'm going to have to drop that from 100 to about, say, 16. You'll see why, and then grid on. Now watch what happens if it runs. There. All right, 6, so let's do this. Let's redo this one. Instead of 16, we're just going to go to 6 so I can blow it up. And watch. Hold. Didn't it go? Oh, sorry, just hit it. You all see that right there? Now, when you look at that, let me bring this window over here. That looks like there's some similarity, but it's anything but exact. Do you agree with that? It's because the values between the sample spacing, we went from 0 to 16 as our range, but we only got, 2 to the 8th, I'm sorry, 2 to the 4th or what, 16 values, right? So they're separated by 1 second. Think about it. First value is at e to the minus a0, or e to the 0 is 1, right? Next value is e to the minus 1. That's a huge change. That's what? Only 37% of the original sample, right? The first is at 1, the next is 0.37. So you don't expect a good comparison. It's somewhat, at least you can see trends. Now, and by the way, the blue is the actual DTFT. This red right here is the adjusted DFT. I mean, the green, or this one, this bluish thing is the Fourier transform. And it's analyzed at the point selected. You'll notice the Fourier transform of 1 over A, which is 1 plus j omega when omega 0 is 1. Right? But here this is skewed. Now watch what happens. Now instead of 4, I'm going to go to, say, 16 sample. No, I'm going to go to 8. I mean 2 to the 8th. And here I need to extend the axis. Good. Let's see, go to, yeah, I can go to 100, I think. All right, now you see up here at the high end, there's some discrepancy, but the low end, they're starting to coalesce. Do you all see that? Everybody? Now watch what happens when I do it 2 to the 10th. Let's see if I can blow this up a little more. See it? Let's go 2 to the 12th, or I mean make 2 to the 12th. By this time I think it's going to be indistinguishable. See what's going on here, guys? This is real important. Now we can actually get sample data, finite interval time, sampling, and if we adjust it by that factor 1 minus e to the minus j omega, adjusted omega times ts, divided by j omega, where omega is adjusted. Now we literally have the Fourier transform of that signal that we can look at. That's very important. What else can we do with that if we have the Fourier transform? Get the inverse Fourier transform if we ever need to, right? So we can take this information, stick it through any kind of filters we want, and we can see, then pull it back to the time domain to see what we have. We can analyze a lot of stuff. The real thing I'm trying to tell you here is this will allow you to look directly at frequency domain information as if it was a Fourier transform, even though it's a finite signal with a lot of other crap in it usually, and you'll get noise and stuff like this. But this is pretty clear that it shows how amazingly similar these two are when there's the frequency of sampling is high enough. You follow me? Now, that's one. I asked, there's several others I did. Now, if I take this signal right here, instead of had this, suppose I take this times a cosine of, say, 10 times t. Now, what would you expect to happen if I did that? Think about the natural property of modulation. What does modulation do? It takes the original Fourier transform and it displaces it or centers it out at a frequency of omega naught. What is omega naught? Looking at that? 10. Do you follow me? Let's see what happens. I got to tell you one other thing with this. Because it's MATLAB and it's a vector thing, I have to put, I believe, a dot here. And the reason, I'll get to that dot, but that has to do with the, see, when you multiply matrices or vectors, you remember a 1 by n has to be multiplied by n by 1, and it gives you a 1 by 1 at the end. Do you all remember this? Well, if you want a 1 by n multiplied by a 1 by n, you put a dot there, and that means element by element multiplication. I'll say more about this later, but you're going to understand with MATLAB there's going to be these type of things. I think this will work. And I say that because, do y'all see that, guys? This is now what we get with that cosine. You'll notice it's right at 10. You with me? I didn't adjust the continuous time Fourier transform. I'm just showing you. Now, the minute you see that in the spectrum analyzer, you know your primary frequency is going to be at 10, at omega equal 10. Or F is that divided by 2 pi. Are you with me? In the speaker, and when you look at a signal on a spectrum analyzer, has anybody done this besides Jeff? Well, I do it. I mean, you're going to do it regularly in certain, I mean, if you're a Wi-Fi engineer, or if you're doing any kind of radar work, or EMC, or compliance engineering, or anything that has to do with data analysis, information theory, you always look in the frequency domain, and when you see these peaking right there, you get a lot of other jitter around there. That tells you that the center transmit frequency is there, or there's a strong component of frequency there, either wanted or unwanted. Now, let me just do something also. If I take this and don't make it cosine, but cosine squared, then what you're going to do is get periodic stuff all through there, because a cosine squared, I shouldn't say all through there, but you're going to get several peaks, and I'm going to try to do this. I can put an absolute value to it. I think I'll try ABS first. I think this one will save me a little a problem. Let's see what happens here. All right, that's not real clear, but you see there's a strong frequency component here, then one here, and you can see one there. Do you all see that? If I square that, the problem is I have to put I should have done, I think I can do this here. I think I can get away with this. I'll stop there on this one. What do you think happens if I do this, if I put a T there? Anybody? But what is it going to do in the frequency domain? Think about it. We know it takes the derivative of that function, right? Of the frequency domain function with a J in front of it. What would that look like, do you think? We can take a look. Let me suppress this other stuff. I'm going to get rid of, here's another thing I do all the time. I don't want to lose that, so I'll copy it and I'll put a little percentage sign in front of it. That means it's not used. Then what I'll do is simply get rid of this, because that part's just the real Fourier transform. And take a look at this. And here I got a real strong component at 10. And nothing else. And if you remember, when you take the actual Fourier transform of the e to the minus at times cosine of 10t, you're going to get that strong component there, and when you take a derivative, it'll be even stronger with the t in front of it. You'll see it's even clearer. Matter of fact, if I get rid of that, I think you'll see it here. Plot. One other thing. If you wanted to see over the entire frequency range, you could put max of omega there and do it. And it's way down here at 10. Make that, say, 100. See what it looks like. Now we got 2 peaks. Make it at 300. There's 300. I wanted to show you guys this because I figured, I know this is valuable, and I know if you haven't done it, you won't probably appreciate everything. A few other things I want to show you with MATLAB, because you're going to be using MATLAB all the time. Here, this is called a workspace. I don't ever write code in here. All the code I write is it's called an M file. If you want to do that, you see how it has new script up here? You just punch new script in the beginning, and every time I create a new script, I type CLC right off the bat. That makes sure the workspace goes clean. After that, usually I put close all, and then clear all. That means nothing's in memory. I get rid of anything in memory, because you can have something in memory you don't realize is going to be used over and over again. I'm just telling you that. Sometimes you can even define things that are predefined, like pi, as instead of 3.14155, you might have it defined as 12 for some odd reason. And then it keeps using that, and all your calculations are messed up. So I do that. After that, here's a few other things I've got to show you with MATLAB. And I'm going to do it here. It's a matrix thing. So if I want a matrix, say I want a 2x2 matrix, and I want it to say 1, 2, that's the first row. A semicolon brings it to the second row, and I'm going to have 3, 4. Now you'll notice I'm using these actual brackets, not curly brackets or parentheses here. Now when I look at that, see how 1, 2, 3, 4. Right? The columns are 1, 3, 2, 4. If you wanted the transpose of that, this is the transpose. Now what happens? The columns and rows are reversed. That, you know what a transpose is from your linear algebra, right? Now, if I take A, just watch this is important, times A is a 2x2, right? Times A is a 2x2, I should get a 2x2 out, and indeed I will. I want you to watch this. Now what that did is take the entire row times the entire column. It took first row times first column, then first row times second column, then for the next entry at the 2, 1 point, take second column, first row. The final one, it takes second column, final row. But watch what happens when you do element by element. What I'm about to show you, element by element, it takes the A11, or the first entry, and multiplies it by only the first entry. It's not row column. So please watch this. If I take A, and then I put a dot here, times A. That dot means it's going to do element by element. First element times first element, then second element times second element. It goes down third element times third element, fourth element times fourth element. Watch. You'll notice if I take 1 times 1, I get 1. If I take 2 times 2, I get 4. 3 times 3, 9. 4 times 4, 16. You all see that? Whereas if it's row column, what do I get? 7, 10, 15, 22. You understand that, class? That's real important. You understand that when you do matrix work on these things. I could probably tell you a few other things that are going to be helpful, but normally what I do is try to omit, when at all possible, writing for loops. What I like to do is do vector, like you saw how I had t equal linspace from 0 to tf, and I had a certain NUM number of that thing sliced up. Well, it creates a vector of t. Suppose I want to create a vector of t here, and I say that t is equal to, now I could write a for loop, and I could say for I equals 1 to 10. Then I could say t equals some tf, right, divided by 10, and then go through t, 1, 2, 3, 4, 5, 6, and index it. But that's foolishness. I will always do a linspace, and now I want a linear spacing between 0 and say 10, and maybe I want 100 points. So I do that. And I want to look at the first value. Say if I want t of 1, I can do it just like that. That's the first value. And if I want t of 100, which should be 10, that would be the 10. Follow me on that? Well, now the thing in parentheses is the index. With me? Let me tell you one other thing that's useful. You know, you might not want linear spacing. Suppose you want logarithmic spacing. Then you can go here, and I can say instead of linspace, I can have log space. Now it's logarithmically spacing the values from 0 to 10, and it's going to have 100 points. Actually, why don't we do 0 to 1,000, and maybe 100 points. Now watch, when I do that, then if I look at the value of t of 1, it's 1. And t of 2, it's that. Wait a second. You know what? I'm glad I did this. The last part, see where I have 0 to 1,000? The next part is going to be, since it's logarithmically spaced, 10 to that number. So if I put 100 there, that's 10 to 100. Let me just show you this. Let me go break it down this way. Suppose I have 10, comma, 1. And let me take this up. I have only one value. All right, that's logarithmically spacing from 0 to 1. You have 10 values. Anyway, you can play with that. That's logarithmically spacing things. I had that as a list to do, to put that up there before I go on to the lecture. I hope this helps someone, just exposure to this. And if you have questions on this, ask me. I'm going to give you a MATLAB assignment. That's the reason I spent on this, that I will collect, and it will be for extra credit. I'll add that in, all right? That's the main reason I did this. Now, get on with my lecture. I know you understand. comparison of continuous time Fourier transform to the actual DFT. We'll do the fast Fourier transform stuff later. Any questions at all? All right. How many had that test again? Over half the class. Now I'm going to show you something I consider real important. And here's what I'm up to today. Yeah? What's that? Yeah, which one? From last homework? All right. Which one?
The first problem.
Tell me what it is.
Compute the DFT of the following signals and x of n is equal to 0.25.
Really a quarter, right? The end, right?
At least 0.25 4 times.
Oh. So it's really 1/4, and it's multiplied by 1, 1, 1, 1, right?
Where n equals 0 to 3 and 0.
It's just got a value of a quarter all the way, right? Well, this is one thing I was going to show you. You can actually get the DTFT of a function and then simply sample the DTFT at the points associated with the DFT to get it. But I'm going to do this one just, you can brute force this. If you look at this, this is the first value, right? It's really a quarter, but that's the 0, where n equals 0. So you go through it, and x of 0 is really what? Isn't that just the summation of all those? It's the summation of 1/4, right? That's the value, and this is going to be for n equals 1, or really 0 to 3, so that's going to be equal to 1. Isn't it, class? Just add them all up. You know, for the DTFT, in case you forgot, x of k is equal to the summation n equals 0 to n minus 1, where capital N is the number of points, of x of n, right, times e to the minus j, and then there's going to be 2 pi over the number of points, and this whole quantity to the nk power, right? So when k is 0, that term is 1, right? And since this term right here is 1, because k is 0, anything to the 0 is 1, I'm just adding up all the values, which would be 1. I hope that's the answer given. Is there an answer given? There isn't? Well, here's how you can get it even faster. If you want to know what this is, on MATLAB, you can just do this. Over here, this is with MATLAB. You simply type in that caret, just x equals brackets 1/4, comma, or not even a comma, 1/4, or 0.25, 1/4, 1/4, and then capital X, you can call it xk, and just equal to FFT of x, and you'll get it. And it'll just show you xk equals, and it'll put these things down. That way you can test it. Does anybody have MATLAB on your computer now? Here? Well, you can check. That's 1. What is x of 1 going to be, class? That's the summation of what? It's just 1/4, right? And it's times e to the what? Minus j 2 pi over 4. There are 4 terms, or pi, right? Over 2. To the n, k is 1. Isn't that it? Class? Well, that 1/4 is there, so I can take it out in front even. That's n equals 0 to 3, so it's 1/4. Now look at this. This is the summation of what? E to the minus j pi over 2 to the nth power, n equals 0 to 3. Add them up. What do I get? 1/4. E to the minus j pi over 2 to the 0 is 1, plus e to the minus j pi over 2 to the 1 is what? Minus j, right? E to the minus j pi over 2 to the 2 is minus 1. E to the minus j pi over 2 to the third is plus j, isn't it, class? What's that answer? 0. Do this in MATLAB. Did you do it?
You beat MATLAB because it's still starting. I'll let you know.
Gotta do something. What's 2? You can brute force it, but I'm gonna show you a trick on this if I have time. Just do it. What happens? Isn't it 1/4, right? Summation of now, what is e to the minus j? Now what? Now that k is 2, correct? If that's 2, isn't this really e to the minus j pi? All right, so I have, what is e to the minus j pi? Isn't that minus 1, class? To the n equals 0 to 3. Just add them up, 1/4 times. When it's 0, it's 1, right? When it's 1, it's minus 1. When it's 2, it's 1, right? And when it's 3, what happens? Minus 1, isn't it? Come on, isn't it? There's a point I'm making. You all see that? What's the value? It's 0. That's 2. What is x of 3? You do it. Just do it. What is it? Now what do I have? I have e to the minus j pi over 2 times 3, or e to the minus j 3 pi over 2, or plus j, don't I, class? So I'll put it down as just plus j. So if I have j to the n equals 0 to 3, what do I get? 1/4, people. J to the 0 is 1. Keep going. Plus j, right? Keep going. J squared is
-1.
minus 1, right? 1. And finally, j cubed is minus j, correct? Isn't that 0? Did you get it?
Agrees, yeah.
So I have basically 1, 0, 0, 0. Now let me show you something that should make this real to you. You all see that looks like a DC signal I'm sampling? Nothing's changing, right? Where do you expect all the frequency domain information?
0.
At omega equals 0 or DC, or x equals 0, capital X equals 0. Is that where it is? Yes. What happens at all the other frequencies? Nothing. There's no information up there. Understand, class? So that's the moral of this, yeah.
I was gonna ask, like writing it as a DTFT from that, would it just be 1/4 plus 1/4 e to the negative j omega plus 1/4 e?
Yes, you're taking the constant now into there, though. You're putting 1/4 inside, right?
Yeah.
Instead of just, I like to take, if it's a constant times anything, take it out in front. It just is irritating to rewrite that over and over. All right? Let me do one other thing too, people. And this, I'm trying to do this to help you. Because I know a lot of this, unless you're writing programs and you see it, like I try to make it really, it doesn't sink in. So let me show you one thing about this. Now, we spent time with the DTFT, and now the DFT. So just watch this. When I look at the actual definition of x of omega, this is a DTFT. Write this down. That's a summation technically from n equals minus infinity to infinity of x of n times e to the minus j omega n, right? Isn't that right? Now, what is the DFT? X of k here is a summation. Now the range goes from n equals 0 to n minus 1, where capital N is the number of samples, right, people? Please watch this. Agreed? It's still times x of n, right? But now this becomes e to the minus j, and it's 2 pi over n, and it's to the nk power. Now I want you to look at this carefully. And you'll notice one thing, that when I do this, if I have like, suppose I have a function and I have something where I have a pulse function of 2b here of n. You know that's centered at 0 and it's got a width of 2b, correct, class? Or I should say it goes from minus b to plus b. All values of 1, correct? We know if we have that, we know the transform of that in the frequency domain, don't we? Remember we did this one class, the pulse, what did we get? We got that sinc function, what? The sinc of omega times what?
Tau over 2.
It's gonna be omega over, well, omega times quantity, well, omega over 2 plus 1. Remember that crazy thing? It was what? The sinc, it does this thing, the sine of, and it had omega over 2 plus 1 over what? The sine times n, pardon me, I should say. Yes. No, I'm over. What it does is turns this into basically a sinc function, but it's the sine of n over 2, n plus 1 over 2 over the sine times omega, pardon me, times omega, divided by the sine of omega over 2 down here. Do y'all remember that thing, that sinc function? It was that sine, the sine of n over 2 plus 1, depending on how they write it in the book. Can you take a look in your book and tell me exactly how they have, what form they have this?
We did it differently. We had some B plus a
Yeah.
half.
All right, I
There
put
was
the
a
B in there.
plus and a half.
I'm sorry, I'm using n there, it's B.
Oh,
Sine of, go ahead,
B plus a half,
right,
times omega on the outside.
yeah, all right, my bad. And this is over sine of just
Omega half.
omega over 2, right?
Mm-hmm.
All right, now, this is very similar to the sinc, but now that we have this, just listen to me, all right, and I'll be done with this very shortly. If we have this, we notice the pulse width is 2b, right? Well, if you're doing this, and now I'm not going to be able to do this because now I have to skew this, but I'm going to show you next time where I can literally take the value 2 pi nk and equate it to simply omega n and find the value of omega that corresponds to that. Basically, when I equate this to this, what you're going to see is the n drops out and omega is 2 pi k over n. Follow me that? It's going to be 2, omega here will be 2 pi k over n. You find the DTF when you have two functions. I'm not going to get this in. I'll show you next time. I'll show you next time. Now, in light of the fact, for this Friday, what I'm going to do is collect the homework. All right, instead of a quiz, I'm going to give you one. It's going to require some programming. Follow me on that? In other words, the stuff I've been going over today, you're going to be required to do, but you're going to be doing a program of comparison of continuous time Fourier transform to DFTs or FFTs, and also possibly something with a TTFT that I'll give you. And I'm sorry I didn't have time to do this.